Hello, everyone. Welcome to the third lecture of the course. Today, we are going to study numerical code for the representation of geodesics and the computation of intensity profiles of accretion disks, various examples, 3 examples, as seen from the North Pole. Okay, the observer will be at the North Pole. So you can imagine that you are looking at Saturn, but from the North Pole. So you see the rings of Saturn, okay? And the situation, the rings of Saturn represent the accretion disk, okay? And you don't see Saturn because it will be a black hole, okay? This is the situation is depicted here. So this is the disk of the black hole. Here we have the photon sphere. This is 3M. And the accretion disk is represented in this vertical plane. Okay, this is the South Pole. This will be the North Pole, and the observer is here very far away. Okay, I'm only representing. This is basically the result of the tracing of geodesics, of many geodesics. All these green curves are these geodesics. Okay, but from below we also have, and they are deflected upwards. Okay, so and as I explained yesterday, we had some weak deflection. These ones that the limiting is this one that goes parallel to the vertical axis. Okay, I don't know if you can see them clearly, but anyway, we will see them in more detail later. And so this is basically the basic sketch of what we will find, okay? So now this is the result of a numerical integration of our equations with many details, okay? The direct emission is green, orange is lensed effect. So these are the geodesics that intersect the axis, the plane, twice, once here, and then they come here, and they cut the accretion disk again here. So this means that a photon that is emitted southward then is deflected and moves northward to the detector, okay? And these red geodesics represent strongly deflected light rays, and they intersect at least 3 times. One here, another here, and then here, okay? And there are other nearby geodesics near this red one that can even make more turns around the black hole. And in the limiting case, we would have this yellow dust line representing the orbits that would orbit an infinite number of times. So would be in circular orbit around the black hole, okay? So this is a summary of what we already explained. And now I will show you how to do that, how to compute these things with this code and the strategy to follow in order to represent a detailed plot like this one, okay, with the different sections split in parts. Okay. So first thing is to set up the equations. Okay, for simplicity, now I'm considering the Schwarzschild geometry. Okay, so I define this function here that represents the Schwarzschild metric. So we have we are using this module to define a function that are the equations of motion. The function that we are defining is at the end of these brackets. And this represents the local variables. Okay, we have the spatial coordinates, the momentum coordinates, the covariant form of the metric, which is here for the Schwarzschild. Okay, it's diagonal, it has the usual representation, the spherical sector. Okay, then the inverse metric, which is here computed simply as the inverse. And then PI represents the components of the momentum, the form momentum, covariant for momentum, okay, with the index below. So the first component is minus the energy. We will set the energy, this quantity is as constant. We will set it to unity for simplicity. It's just a normalization or choice of units. and then the PR, P theta, and P phi momenta. And the Hamiltonian is simply the scalar product, this contraction, this quadratic product of the momentum, the inverse metric, and another momentum divided by 2. Okay? And once we have the Hamiltonian, right, that only depends on the inverse metric, so if you want a different model, just replace this. Okay? The Hamiltonian equations are written formally in this manner. Okay, this is for the radial component, for theta component, for the phi component, and then for the momenta. Okay, it's that simple. These 6 equations represent our equations, and these are functions, functions of the coordinates and the momenta of these variables. Okay, so you know that Mathematica has some internal structures and some way to handle functions and numbers, and in order to make calculations faster, instead of inserting these equations in the differential equation, what we will do is to insert in the differential equations numerical versions of these functional expressions, okay? Because evaluating functional expressions is slow, but evaluating numerical functions is simpler, okay, and faster, more efficient, okay? Mathematica is optimized for that. So, and this is done in this way, okay? You just need to learn this command, okay? We define the list of variables, which is a vector, in this way. Our functional expressions now evaluated numerically using this command, okay? This is how is the mathematical syntaxis. You just need to learn, and that's it. Okay, so this defines the equation. So let me quit. Okay, and now I evaluate this module. So we have defined the equations. Okay, it takes a while because I'm loading the kernel. Okay, maybe today it takes a bit longer because I'm recording. But anyway, so let me go on. Now that we have the metric, the Hamiltonian, and the equations, we we set up the numerical integrator for one geodesic. Okay, we are going to integrate one geodesic. Okay. So, and this function, this integrator for one geodesic, has these input variables: the initial conditions for the equations, the maximum value for the affine parameter. We are integrating with respect to the affine parameter, and now two complementary elements: if we want to print the geodesic or not, if we want to plot it or not. Okay, and this is the color. You just choose the color of the line that represents the path of the geodesic. Our local variables are here: the variables, the equations, the initial conditions. Sol is the solution of the differential equation, the affine parameter. Then we have a counter of the number of intersections of the geodesic with the accretion disk, with the equatorial plane. This is lambda final, and this is the point where the locations at which the geodesics intersect the accretion disk. Okay, so the variables are these ones. Okay, we already know they are all functions of the affine parameter, and so we define the equations in that manner. The derivatives of our variables with respect to the affine parameter, and those derivatives are equal to the numerical values of the functions that we define here, okay, of the differential equations. That's it. It's very simple. So now we have the equations. The initial conditions is something that must be given at some point. Okay, and yes, and that corresponds to the evaluation of these variables at the initial time when lambda is 0. We set this lambda 0 as the initial time for the differential equation. And cut points, as I said, is an empty vector, okay? And this cuts counter is something that is set to unity at the beginning. And We will understand the meaning of that in a second. So it is initially set to 1. So now we start the numerical integration. So for the numerical integration, we use the ndissolve command of Mathematica. So we give the equations that have been defined here, the initial conditions that are defined here, and then yes, the initial conditions are given from outside. Okay, when we call the numerical integrator, we must provide it with these specific initial conditions, okay, which appear here. Okay, well, so they are here. And then we use this command when event. This is very useful to extract information or give from the numerical integrator or give instructions to Mathematica about when to stop the integration. In particular, this first when event starts here and ends here. Okay, this is telling us that if the radial function is very small, is close to the center, so don't wait for the code to crash. Okay, simply stop the integration smoothly. Okay, so it's better to stop it voluntarily than to get an error message because then the numbers are exploding because you are reaching the singularity. Okay, so this is just a safeguard. It's something that avoids the crashing of the code near the singularity when the geodesics are captured. Okay. Now, this is the second when event is the one that really matters. Okay, it's the core of this code. It's represented here. So let's see what it does. It works as follows. When the angle phi, well, let me explain this why the angle phi is because we are working, well, in this particular implementation, I'm assuming that since one angle is fixed, okay, in particular theta, the polar angle is fixed because it's 0, the observer is in the North Pole, then the motion takes place in this plane, okay? So this angle, this azimuthal angle that actually it represents the theta angle, so I'm just changing the letter, sorry. So I'm using phi to represent the angle on this plane, okay? This one. It should be theta, but it's phi, but that doesn't matter, okay? It's not relevant. What really matters is that light rays come from infinity, from phi equal to 0, okay? And the accretion disk is located at phi equal to pi halves or phi pi, 3 pi halves, 2 pi, and so on, okay? Depending on the intersections. Very good. So this when event is detecting when the angle phi is on the accretion disk, okay? When phi is pi halves, then we are in the upper side of the accretion disk. When it is 3 pi halves, then it is again hitting the accretion disk from below, okay? And so on, okay? So the condition for intersection with the accretion disk in our case is this one, okay? And then when this happens, then Mathematica does the following. It appends to this array, which we call cut points, which initially was empty. Okay, we have to initialize this array. This is a valid way of doing it, just an empty brackets. Here to this vector, you add the counter that initially is just the number 1. This is the first intersection, okay? And the location of the radius when we are on the accretion disk, okay? So the value of the radius here. So this means that we are intersecting for the first time, because Cat's counter is 1, at this location. And we save this information, this vector with 2 entries, in this cut points array, okay? And then since this has identified the first intersection, we add 1 element. So we add 1 unit to Cat's counter. So Cat's counter now will be 2. So if now we continue the integration of the geodesic and this condition is again satisfied, then cat's counter will be 2, and we will save that new location. If the geodesic keeps turning around the black hole and cuts again and satisfies this interaction, then cat's counter will be 3, and so on. Okay, so we are storing all those intersections with the order of the intersection together with the position. Okay, this is the simplest approach to the problem. Okay. Very good. And that's it. So we have the equations, the initial conditions, some actions that the numerical integrator and resolve has to do. And we are integrating with respect to these variables and in this interval. The interval goes from 0 to Lmax. And this Lmax is provided initially. Okay. Very good. We are using the method, the Adams method for the integration because this is particularly useful or convenient when we deal with Hamiltonian systems. You can use any others or simply let Mathematica use the one that it finds appropriate. Okay. The working precision, this is very stringent. So if you want to do the calculations faster, you just can reduce this to 20, and then the precision go to 10 and 10. Okay, these are reasonable values. Okay, working precision usually is twice as much as the precision and accuracy goals. Okay, I think 20 is more than enough. And the number of steps, this is just for security reasons, but it's more than enough because we are not getting errors and warnings from the integration. In any case, they are quiet. So the Mathematica is not showing the potential warnings in this case. Now, when this integration stops, then this is the location of the final this is the location of the radius at the end of the integration. Okay, and this gives us the final value of the affine parameter. Okay, very good. This is important because when we plot the geodesic, we need to know which is the final value of the affine parameter. Okay. Okay. And this is the geodesic is represented here in parametric form. We call it my geodesic. This is an output. My geodesic is a global variable. It will be shared not only locally, but is something global because this is the integrator of one geodesic, but we will introduce this into a recursive and iterative process. So we need to provide outputs to that to handle all the geodesics. Okay, so and this geodesic, my geodesic is a parametric plot that evaluates in Cartesian coordinates the x and y components of the orbit or the trajectory followed by the geodesic. Okay, as given by this output solved. Okay, and it is plotted from 0, from the initial starting point to the final starting point. But yes, since this is huge, because sometimes I use as lambda the original radius, the original position is usually far away, like 100 or 1000 in R. We don't want to plot such a huge geodesic, okay? We only want to plot some restriction. And for that restriction, we are considering an interval of radius, which is we only plot a circumference of radius 35, which is more than reasonable. This is something you can see here. Okay, so this geodesic is integrated from r equal to 1000 to be sure that we are really far away. But what we represent here is something more compact, the region that is really relevant for us. This contains enough the relevant information. Okay, this is why this is restricted to a circumference of, in this case, is 30 units. And now I'm just considering 35. Okay, just to be consistent, let me put here 30. And that's okay. So we are just plotting this region. and with the color that we chose, these conditions, and blah, blah, blah. Okay? So that's it. We have the equations, the Hamiltonian equations. With those equations and given initial conditions, which I haven't discussed yet, we can integrate one geodesic, store the intersection points in this vector, cut points. This is a global variable. This is why it appears in blue here. And we also have as global variable my geodesic. So the plot of the trajectory of this single geodesic. Okay, so we have the geodesic and a vector with the intersection points. Okay, very good. So now the next step, obviously, is to implement this computation in an iteration process for many geodesics. Okay, and many depends on what we want to do. Okay, as I will show with examples in a moment. So this is our ray tracer based on the NDSolve integrator. Obviously, if you want to change the NDSolve by a different integration routine, you can do it. Okay, just replace this part and that's it. And so our ray tracer needs as information the mass of the black hole, which usually we will give set as unity, the energy of the photon that will also be set to unity, the impact parameter. Remember that the impact parameter is defined as LC, which is constant, divided the energy of the photon. And in this case, the energy of the photon is the variable n. This En. Okay, this is the impact parameter. So here, what we are doing is giving an interval of impact parameters. From some initial impact parameter to a final impact parameter, we are going to obtain geodesics in that interval of impact parameters. And the number of geodesics in that interval is given by this. Ng is the number of geodesics. Okay, here, this is a command that allows us to print the plots or not, depending on our interests, and the color, okay, because it is always nice to choose the color of your geodesics, mainly because this classification looks more transparent in colors, okay? One family of geodesics, these are the direct image, in orange, the lensed image, and so on, okay? That's why the color is useful. Okay, so here we are. Now we have we understand how we call the iterator, this here. Let me go through it. So we have that the local variables is M0, R0. M0 is the mass. As I said, it will be set to unity. The energy 0 local is also it will be unity. This parameter M is 0 here. For massive particles, the code is also valid and must be set to 1. Okay. Probably you need some adjustments at some point. I don't remember if this M is defined in the Hamiltonian equations, but probably it's only for photons. So the initial impact parameter will be B0, the final B1, the number of geodesics is Ng, and we set as the starting point for integration as 100. We could put here 1,000, okay? But it simply takes longer, okay? And you don't really lose much, and so we gain time with this. And the delta between two geodesics is given by this. The final impact, the range of our interval divided the number of geodesics minus 1, okay? Minus 1 because you know why. Okay, because if we want n geodesics, we will have n, not n plus 1. Okay, so this is the way to get n geodesics. And now we generate a list of the impact parameters that we want to study, simply with this discretization of the interval in n geodesics. Okay, and as the maximum value of the affine parameter, I will take 2 times R0. Why 2 times? Because far away, the geometry is basically Minkowski. So a light ray moves at the speed of light. So it takes an affine parameter of order R0 to reach from R0 to 0, okay? And so if the light ray approaches and then moves away, so it is safe to give the same time for it to escape, because sometimes it can be turning around, giving turns around the black hole for a while. So it is not, it is good to be, to give enough time for the integrator to complete the integration of the geodesic. Okay, so now that we have these parameters, we define these lists of information, okay? This is the list 1, list 2, and list 3. What does this mean? The first list stores the data of the direct emission, okay? This means that the radial positions, given an impact parameter, if we start the geodesic from an impact parameter B, when we propagate backwards and intersects for the first time on the accretion disk, we save that pair, the impact parameter and intersection point, in this cat list 1. Okay. If that geodesic has a second intersection with the disk, then we save that information here in the second list. And if it has 3 or more intersections, they are stored here. Okay. In that way, we can split all the luminosity and the different intersections in this classification: the direct emission, the lensed emission, and the contribution mainly coming from the photon sphere. Okay, very good. So now that we have this initialized to 0, the information, the relevant information, note that they are in blue, so they are global variables. We will use them for extract information later. Then we set the equation. We call the equations of motion, okay, for these values of m and the energy of the photon that we will set to 1 and 1, okay, for simplicity. And then we start the proper iterative process of integration. So all the parts, all the integrals. We make a table with initial data, the initial impact parameter, and since remember that we have a table with the list of impact parameters, okay? The initial L is 0, the final is 2R0, these are fixed. And then we define the initial data for the numerical integration, okay? And the initial data, in our case, is the distance from the center of the black hole to the detector. Pi halves is well, actually here I'm in the equatorial plane, but that doesn't matter. It's just a reference angle. And this is the actual size of the point. Since R0 is 100, that is not 1 million. So it's just in the previous lecture, I was saying that the direction is always the same. But here it does depend on the impact parameter and the distance, because this is taking into account a small, the effects of having the detector not too far away from the black hole. Okay, so since now we are at the distance R0 for the 100, and the impact parameter is approximately 10, so 10 divided 100 is 1/10. Okay, so it's not really 0. Okay, so just to take into account that detail, so we consider the actual size of the object. So there is a small phi angle from which the geodesic emanates from the detector. Okay. This is for the radial spatial part. For the momentum parts, the radial momentum is given by the Hamiltonian constraint. And note that the parameter m is really taken into account here. So you can consider also massive geodesics, okay? We are considering photons, but if you put m equal to 1, the initial conditions are certainly considering also massive particles. And I'm choosing all the units in terms of the mass of the black hole. Okay, this is where everything is multiplied by m0 here. is just because of the units. Okay, if you change the units of the black hole is not just one, then you need to rescale everything in this way. Okay, so this is consistent. But for simplicity, just put m0 equal to 1 and that's it. Okay, and now that we have this vector of initial conditions, okay, we call the numerical integrator of one geodesic. Okay, this is the one that we define here. Okay, it needed the initial conditions of the equations, L max, whether we print or not, and the color. Okay, and remember that the initial conditions that we give is what appears on the right-hand side of the variables evaluated at lambda equal to 0, which is the initial starting time, affine parameter. Okay? So now we give this information to the integrator and it computes one geodesic. The geodesic that is defined here from the list of geodesics takes the different values of the impact parameter and it starts evaluating the integrals. So it computes the geodesic path and saves the intersection points. Okay, this is the information that we get. And now, once we have integrated the geodesic, we process the information. Okay, and we do the following. If the geodesic has some intersections with the disk, okay, so the length of that vector of cut points is not 0, then distribute the data, okay? And the distribution is the following. Cut points, if you remember, it's written here, cut points is a vector that contains, it's an array that contains vectors, pairs. N is the order of the intersection, and Rn is the location at the accretion disk of the intersection. So when N can be 1, 2, or 3, okay, or even higher. But we are classifying things in 3 classes: 1 intersection, 2 intersections, and 3 or more. Okay. So when this vector C here has 2 components, C1 and C2. C1 is the order, okay? So when the order is 1, so in the list 1, you save the impact parameter and the radius of the intersection. If the intersection order is 2, then you save that information in the second list, okay? And if the intersection is 3 or more, well, actually only 3, you save it in the third list. Okay, so we are classifying the intersection points in the different kinds of light rays: the direct emission, the lensed emission, and the photon sphere. Okay, and then we save also the geodesic. Okay, and we do this process for all cut points and for all the impact parameters of our list. So this table is doing the iteration of all our geodesics. And for each geodesic, generates the plot and stores the different intersection points in different lists. Okay, so everything is well organized. Okay, and now at the end, just once we have finished doing all these integrations, this iterative process, this function decides if we plot the geodesics or not. Okay, if we wrote 1 for print plot, okay, remember that this is print plot is an input, so we say if it is 1, then we plot the geodesics. If it is 0, we don't need to plot them. Okay, at the beginning, as we will see, it is important to plot them. Okay, so you will understand how this works. After a while, you don't really need to plot them. Okay, and this speeds up a little bit the process. Okay, so if the print plot is 1, then show all the geodesics, all paths. All paths is saving all these geodesics. Okay, and well, it prints the geodesics in some way. Okay, If we set print plot to 0, then there is a warning, a message that says that no plots requested. Okay, that's it. Okay, so this is the structure of this notebook. This is what we really need to compute the geodesics. Set the model with the Hamiltonian equations, integrate one geodesic, and then set an interval of impact parameters to plot several geodesics, NG geodesics in that interval, okay? And extract the data and save them in different lists. We will have 3 lists of data and a list of plots of the geodesics, okay, which is here in all paths. This all paths is also global. Okay, let me execute this one. No, this was, I need also to execute this one. And now these 3 functions are charged in memory. And this is how it works. This is an example of use in Schwarzschild. So this is ray tracer. Remember, this was the mass of the black hole. This is the energy of the photon. We set them to unity. This is the initial impact parameter. This is the final impact parameter. This is the number of geodesics that we want to plot. This is whether we want to plot or not. Okay, 1 is yes, plot. 0 is don't plot. And green is the color. Okay, and if I execute this command, we get this. Okay, okay, very good. I'm lucky. I'm very lucky because look, this geodesic that comes from far away with an impact parameter that originally was 20. Okay. This is slightly deflected or weakly deflected, but this one, okay, this one is almost parallel to the vertical axis. So this is indeed the one that we wanted to separate the direct image from the lensed image, because the lensed image is represented by the geodesics that cut the axis twice, once here and once here, or very far away, okay? So this is possible because I've been playing before with the code, okay? Because initially, you don't know where these regions are, okay? So you start exploring like between 20 and 18. And what you get is this thing, okay? This is why I'm only plotting 3 geodesics, okay? Because it is convenient to visualize them. So if I reduce from 8 to 7, I see that it is deflecting a bit more, but it's still not parallel to the vertical axis. So I keep decreasing this, like for instance, like this. It's improving. Then we reduce a bit further. It's not yet. We play a little bit like this, okay? And then finally, more or less, okay, we don't need to get the prize to be the most fine-tuned geodesic plotter in the world. 6.15 is more than reasonable. Okay, this is a good limiting value. So any geodesic from 6.15 upwards will be in the family of direct image, okay? Because they only intersect the axis once. Okay, this is why I'm plotting the geodesics, because first I need to explore the range of parameters of my geometry. Okay, so now that this range is clear, I move to the geodesics that intersect at least twice. This is the optimal interval. Okay, as you can see, let me change this like 5. Okay, and you see in this interval, this one is the one that is telling me how far we are from the limiting case. Now, if we reduce to 3, we get that. If we put here 0, we went too far because this one has been captured. Okay, so this is not good. So maybe it was 2. Yes, 2 is reasonable. You can even put here 9, and it's a bit more, no, 7. It's a bit more parallel. Not quite, but probably 75. Okay, you see how it goes, no? So you can play. You need to play a little bit with your geometry to identify the range of parameters for the impact parameters. Okay. And so these are the ones that cut twice, once here and once here. Okay. And this will cut again at infinity. Okay, now the light ring represents those geodesics that intersect at least 3 times. So we have all the 3 come from this direction. They are almost degenerate. We will need to magnify a lot this region to be able to see that they are really 3 different impact parameters. But when they get closer to the horizon, not to the horizon, to the photosphere, then they are deflected in clearly different angles. Okay, we have this one that goes almost vertical. Okay, note that this one here was 5.2275, and our starting point here is 227. Okay, so that's why this is a little bit inclined. Okay, so very far away, it will intersect the axis. So we have the first intersection, second intersection, and this one will be far away. Then we have this one. This third intersection is clear. Okay. And then what do we have? Well, this one is doing this, and coming back here. Okay, let me see if we can see the points. No, it doesn't let me. Okay, but this is making four intersections, basically. 1 here, 2 here, another here, 3 here, and this is the 4th. Okay, this has 4 intersections. Because look, the critical impact parameter in Schwarzschild is square root of 27, and I'm very close to that. Okay, I could improve it. If we get closer to -5, that one will move significantly. It's giving more turns. So, but sometimes it's difficult to distinguish how many turns. Okay, so it's good to get the 4. Is very illustrative. Okay. Very good. So now you know how it works. Okay, so we have this characterization, and then we need some additional any geodesic below that, below the critical parameter. It's like 1 minus instead of 1 plus. Here we have 1 plus, so they are above the critical parameter. These are below. These ones are all captured by the black hole. Okay, they eventually fall into the black hole. So in this region, well, it's clear that the starting point is just below the critical parameter, and then we go very close to the center. Okay, very good. And now that we have identified these intervals, okay, we can increase the number of geodesics to extract information, more data, okay, because we need to populate the list of data, okay? And this is something that we do here, okay? I will consider the previous intervals, okay? From 20 to 815, 814 to 615. These are in green, okay? And I'm representing 50 geodesics in each case. I'm not plotting the geodesics because now I only want the data, the list of data, not the curves. The geodesics are useful here to identify the different intervals graphically, visually, okay? But then to build the intensity profiles, what we need are relevant, informative intersection points, okay? With 1, with 2, and with 3 intersections, okay? So we will need to populate those intervals with many geodesics, okay? Particular for the orange region, we have 30 here, another 30 in this small interval. For the red region, yes, this is a very small interval, and we put on 30 geodesics there because we want at least 30 points in that list, okay? So let me execute this because this takes a time, okay? So this is the heaviest part. Even so, it's not too slow. We are now accumulating the data. And once we have the data, okay, I will show you the list. We are joining the different lists, okay? In the list 1 inherits the previous lists, okay? So initially they are empty, okay? and then the first integration populates the list 1, list 2, and list 3. The second integration adds the new points to that list. So we are populating or adding data to those lists. And then the result of those lists is represented here in this diagram. So this is the collection of impact parameters and intersection point. Okay. What does this mean? Well, this means that, for instance, for the impact parameter B, approximately 12, the intersection with the accretion disk is at 11.1. Okay, because the deflection is weak. Remember here, okay, this external geodesic, the deflection is relatively weak. Okay, so from here to here, there is a small decay. Okay, it's a small size. It's not exactly the impact parameter. It's not a straight line. Well, it's like a straight line, but with a small a slope that is not 1. Okay, and so this. Let me go back to this plot. Okay, so this range of impact parameters only have one intersection with the disk. These are the direct image. Then at this point, you see from here, for this impact parameter 591, we have points in the second list, the orange, okay? These are light rays that intersect twice the accretion disk. But and obviously, if they intersect twice, that's because they already intersected before. So they intersect one and then twice, okay? And near in this region, we have light rays that intersect 1, 2, and 3 times, okay? But note that this interval, the red line, is really narrow. It's very thin. This was evident when we draw the plots here. The red region, this interval is very narrow, okay? But it leads to 3 intersection geodesics, okay? Very good. And these are called the transfer functions, okay? Because they will generate, they will add, they will map the intensity profile, the emission profile. It will be mapped through these functions into the observed image, okay? Because this means that we will get photons from here, and from here. So there will be regions that receive 3 photons with different redshift and different locations, okay? But which have the same impact parameter. So, and remember, the impact parameter is related to the pixel on the screen, okay? Yes, here, since we are looking at the black hole from the North Pole, the screen is only, the pixels only depend on the azimuthal angular momentum, the impact parameter LC divided E. And each value defines a circumference on the detector, okay? This is why we only need one parameter. We don't need the 2 coordinates alpha and beta that we were discussing in the previous lecture, okay? Because alpha and beta are equal here. Well, they are not equal. It's a radius, okay? The impact parameter is a circumference. Okay, now that we have this, we have all the information about the geometry. We know what the geodesics do. And now what we do is to introduce different profiles of intensity to see which regions produce photons and how these photons are transferred to our detector, okay? And for that purpose, we are using the GLM intensity profiles that I presented yesterday with those parameters, the mu, sigma, and gamma, okay? And with specific data, with specific values of the parameters, okay? So we will call the first profile as this one, with these parameters. These parameters, the second profile has these parameters, and the third profile has these parameters, okay? We have 3 profiles, and they are represented here in these plots. Let me execute this. These are the plots. This is the model 3, is in blue. Blue is intensity profile 3. Just, as I said, is this function with specific parameters, these parameters. okay? So this intensity profile represents a disk of particles that is in circular orbit around the black hole and has the maximum intensity at the ISCO. Then the intensity decays very fast. It's basically zero. The second model, this purple, model 2, is a model that is falling towards the black hole, okay? The horizon is here, okay? So this part is not observable. So, but this, and the intensities will be normalized later. So simply that we cannot see much here, but it will produce a signal, okay? And the first model is this red one that also falls, is representing matter that is being absorbed by the black hole. These two are absorbing matter. This is not absorbing matter. This only has a disk like Saturn orbiting around the black hole, okay? And now let me just make some redefinitions of the list of data, okay? The list of data that we obtained here for these plots, okay? I'm just changing the notation slightly to process that notation, that information. Now we produce the redshift factor. Remember here, the accretion disk is a simplification that only has intensity. It is not rotating, okay? It's static. In the next lecture, we will see how the rotation of the disk can be implemented and many other things like the inclination of the disk and all that. But for the moment, to understand the basic concepts, it is best to stick to a static disk. So this is the redshift factor, and then what we do is to take from the first list that contains impact parameter and radius, we build the direct intensity profile, the direct image, which has the impact parameter and the redshift factor evaluated at the radius to the fourth power. Remember that we showed that yesterday, and multiplied by the original intensity profile. So this means that this is the intensity profile measured on the detector at this location of the detector, at this position of the pixel. This is a circumference, okay? This is for the direct image. The length image is given by the same thing, only evaluated on the second list. And the light ring is the third list, okay? So we evaluate this, and this is what we have. Let me show you this in a bit of detail to understand what we are doing. This is the third model, okay? The one that is picked at the ISCO. This is the emission profile, okay? This is the emission profile, but this emission profile, when it is propagated, it can pick photons from different regions, from the direct image, which is the green one, from the length image that generates another peak of intensity, okay? And from the light ring, okay, from the photosphere, that is the red region. So we have this original intensity profile, when propagated along the geodesics, it generates three images, okay? And this is the comparison in absolute values, okay? And the difference in size is due to the gravitational redshift, okay? Because the intensity is lowered by this factor G4, okay? And G4 is smaller than 1. And this Y is the radius on the disk, okay? So that explains the reduction of size. Now, the point is that we need to manipulate this data because here we have discrete points. And what we want to do is to add these intensity profiles. So here I have implemented an interpolation function to generate continuous functions associated to this list of data. Then I plot the interpolated functions in this way. So it's basically the same profile, only that before here, this is a bunch of discrete data. This is a continuous function, okay? And now I add all the functions and integrate them. So these are all the functions. We integrate the total intensity. We add all the intensities, okay? And we integrate everything. So we get this, this quantitative value. that the total intensity, once we compute the sum of the three intensities, okay, and divide each contribution by the total, it turns out that the direct image contains 95% of the total intensity, okay? The lens image, approximately 5%. And the photon ring is very little. It's smaller than 0.2% of the total intensity. We will see that now. Now that we have all the three functions, continuous functions, we can sum them. We can add these functions together to get a smooth profile, continuous profile, and it has this form. And now what I will do is to represent this in a density plot. Okay, so let me see if it works. Yes. And when we represent this intensity profile as an intensity plot, since it takes a while, I'm not going to execute it now, but this is what we get. Okay, so this is what we see in our detector when observing the black hole with accretion disk, with that accretion disk from the North Pole. Okay, so this part here corresponds to this intensity, the direct image, this one. It has a maximum, okay, some width, and then it decays outwards. Okay, this is what we see here. Then we had another maximum with a width and decay. This is the lensed image. Okay, this is, wait, this part. Okay, up to here. And then there is this peak. This peak is represented by the photon ring or the photon sphere. This thin line, I don't know if you can see it. Okay, let me just make it a bit bigger because it's important to see that. 800. Yes, that thin region contains the information of the photon sphere. Okay, very good. So now we can repeat the process with the other two models that I introduced, the GLM2 and GLM1. Okay, so let me go through them. And this is what we get. Now the intensity profiles are different because the properties of the disk changes. The geodesics, remember that the geodesics are the same. Okay, these sets of data are the same. The only thing that is changing, the only thing that is changing is the intensity profile, how we convolute or modulate the geodesics with the specific intensity profile. Okay, so in this case, for this initial intensity profile, the transferred image is this one. Okay, so we need to generate the continuous version of those discrete curves, add them, and then the sum of the intensity profiles is this one. And now we transfer this into a density plot. And the density plot is as follows. Well, it's slow. Sorry, because the time is limited. Now it's charging. Yeah, here it is. Okay, it's very different from the observed intensity profile of the first model. Okay, the geometry is the same, the geodesics are the same. Okay, but the way these photons are transported to our detector gives this structure. Okay, we see here a thin line that represents brighter thin line that represents the overlap of the lensed image and the photon sphere. The photon sphere is always very thin. Okay, and as you can see, the astrophysics of the disk changes completely what we see in our detector. For the third model, we also see here an overlap. Okay, and the total intensity now is this structure. And as you can see, the density plot is also different. You see, there is a brighter and broader line here that represents the lensed image. Okay, and the light ring is also a maximum that is bright, but is internal to that to the lensed one. You see, the lens image is this broad part in yellow, and the other yellow peak is here. Okay. So as you can see, different accretion disks generate different images for the same geometry. So that's where the challenge is for theoretical physicists to extract information about the background geometry for specific realizations of the accretion disk. And to understand where the physics is, where the fundamental physics is, it is useful to compare the three plots. Okay, if we compare the three plots, this is what we get. I have divided the circumference, the plane, in three sectors. And as you can see, each model has a different direct image and lensed image, okay? But what is really common in all of them is the location and width of the photon sphere. You see, it's here. Let me make it bigger. The photon sphere is always there. The photon ring, this one, is in the same location, This doesn't change. So what we need to do is to clean the data. Well, first, from an observational point of view, we need to obtain very high quality data, such that they allow to see the different contributions, including the light ring, okay? And then we need to remove the foregrounds, in the sense that we need to remove the direct image, the lensed image, and then we will be left with the light ring. And here the light ring is the one that contains the fundamental information about the geometry, okay? All the details, the direct image and the lensed image, contain information about the properties of the disk, which is very interesting, okay? From an astrophysical point of view, studying accretion disk is very interesting. But from a theoretical perspective, we are more interested in the parameters that characterize the light ring. And this is the challenging part, because only a tiny fraction of the total intensity is contained here. And it is contaminated by the influence of the other two foregrounds, the direct image and the lens image. Okay, so that's all I wanted to tell you today. And next day, we will have more fun, right? With inclination and those things, and rotating disks. It's fun. Okay, bye-bye. Thank you for your attention.